Good morning, good day, good evening. I don't know. It depends how many people and from where these people are at the moment are. And I'm glad to present second talk of Leonid Chekhov, and he will speak about matrix models and topological recursion. Please, Leonid.
Yes, thank you. So it's a direct continuation of the talk last week, and actually it's the same set of slides. So when Ilya will distribute, you feel free to scroll up and down and coming back to something that were said last week and coming forward to something that I'm going to present today.
Let me say a few words. I'm sorry, Leonie.
Sure.
Can we ask participants to mute yourself? And if you have any questions, please unmute yourself and ask. But
Yes. So feel free also to unmute and ask, because basically that's our intention, to have some learning.
sorry.
So what we'll learn in the first part was just a simple example, simplest ever example of one matrix model, and we obtained that in this situation. So let's come a little up. We have a spectral curve. So I will also now. So given by some equation. So it's, you see, a hyperelliptic equation and hyperelliptic curve in the case of one matrix model. And as I will see on another example today, it's just one possibility, because in general, I will also show that we can actually obtain any algebraic curve using this method. So as soon as we have this curve, we can address the following problem. So again, I cut some angles in this talk, because apparently I have to compress everything in just 2 hours, and it's very hard for comprehension. But I want to present the structure. That's my main intention in this series of talks. So we have this spectral curve, and actually the same spectral curve, it defines, like we can see in this pattern. Oops. It defines, it's actually governs the distribution of what we call the eigenvalues of this matrix H. So this is based on this famous observation that if we have, sorry, questions? Not so far. Okay. So if we have this matrix integral, and this is this Haar measure, so it has basically n-square integration, we can reduce it to just n-fold integration over eigenvalues of the corresponding Hermitian matrix. The only price for this is the appearance of this van der Monde determinant squared, which comes just from a transformation of measures between these two integrations. So, and this happens actually virtually in all cases. For instance, the same, more or less the same structure will be relevant for two matrix models. And what we also can say is that the same spectral curve that we have, it also governs through this this identification due to the dispersion theorem. It governs the distribution of eigenvalues, or to be more precise, an equilibrium distribution of eigenvalues for the same model. And so so this distribution also may span, well, we segregate one sheet in the complex plane of x variables, and which we call a physical sheet. And in this sheet we have we might have several intervals. We might have several branch points, like here in this example I have 4. And in principle, we might consider a situation where this eigenvalue distribution spans not just one interval, but several intervals. Basically, this also means that the corresponding spectral curve, as we know, if I come back to the previous slide, it might have a non-zero genus. So in one matrix model, it's basically the genus is defined by the distribution in the physical plane, because I have just 2 copies of the plane. And in more general situation, it might be that we have one cut on the physical sheet, but we have more cuts on other sheets. So I will not I will not be able to make it in any detail today. But for your reference, so we might have a situation where indeed we have more than one cut and more than one domain of distribution of these eigenvalues. And just to mention again, it's not my intention today, no way, but just to mention that these representations in terms of eigenvalues, they are crucial for addressing a situation when we want to consider some integrable systems related to these matrix integrals. It's also a very old story, so we can also then present everything in terms of the corresponding systems of orthogonal polynomials related to this potential, and consider some bilinear equations for the corresponding objects that are given by these formulas, and so on. So I leave it totally aside today, but I do hope that in subsequent talks on our seminar, we definitely will come back to this. So today my intentions are modest. I want just to present the analytic structures related to this and more general integrals. Okay, so let's continue. So what are the corresponding analytic and algebraic structures? So it's the same picture as we had on the previous slide with just I want to consider it as a complex plane. So around every cut, I have the corresponding closed contour. So here again, it's just a simplest situation where we have just 2 cuts. So I reserve one contour as some reference contour, and I take all other contours, just one in this situation, as a cycles of the corresponding Riemann surface, and the corresponding the adjoint B cycles will be between the corresponding contour here and this reference contour. What also is important is that we also have the contour that actually is the union of all these A contours, including the reference one. And we know again it's just a standard in integral analysis that if we consider again this expansion, and n is considered as a large parameter, so we consider asymptotic expansion in n. Then if I consider just the leading term of this expansion in the free energy, this leading term is saturated by the equilibrium distribution. So it's just given by this functional of where y is already familiar to us, function or differential that is determined by the equation of the spectral curve, and actually all subsequent properties.
Bosnikov was his advisor.
Oops. Okay. I don't think it's relevant. It was a question. So all properties of this leading term of the free energy can be derived out of this expression. And what differs it from a standard matrix model? We also introduce these terms. So basically, we fix these terms serve as they fix the number of eigenvalues living at every interval of the distribution. So it's not exactly, say, we know that if I want to consider just a regional matrix model integral, it's not precisely what we are about to address below, because basically we know that the result will be not just the objects that we evaluate here using all this machinery, but actually it will be presented by some weighted sum of these terms. So again, to be more precise, it's not a matrix model, it's an integral of this sort that we have upstairs, where I actually somehow I have some knowledge beforehand. So I knew approximately where these cuts are situated, and we fix the number of eigenvalues at every cut. So it's just a preamble of what we are about to do. So let's consider the next part, and what are the objects that we are about to study, for the objects for which we are going to make the corresponding topological recursion. So main objects are correlation functions. And again, as always, it's not exactly a function. So, oops. So it's actually is in what follows, we consider them to be differentials. Why? Well, because it works well. It just it's my explanation, my personal. So it's maybe my cursors will not agree with that and have more deeper understanding, and definitely they do. But so just consider it as a definition. So we started, remember that we started with these correlation functions, and they were functions. And now what I do, I just add this differential. So I multiply these functions by differentials, making them differentials themselves. And we consider these sets of totally symmetric forms. And with respect to each variable, it will be just one form. And even for the future, I will mention that basically we expect that, first of all, each of these differentials has a corresponding expansion. Oops, I have to move a little up Otherwise, so we have the corresponding expansion in terms of this h variable, the formal. Well, let's still keep this n. So exact formula is that it's 2 minus 2g again minus m, and then it has all this. Sorry. It's not g. So g is reserved for the genus of the spectral curve, and it's fixed. And so we have this expansion, and moreover, we expect something from the structure of these terms, that for basically for in a situation when 2h minus 2 plus m is greater than 0, which we call the stable condition, stability condition, the corresponding forms have singularities only, well, only at branch points. So this is something that we reserve for future. So, and singularities of some fixed order, restricted. So basically every time we are speaking about finite dimensional linear space. So John has a question, right?
Yes, actually I have two questions. First of all, there are parameters in the V's. So these are the sort of flow parameters, but you only write down the dependence on X. Do you mean to evaluate the integral at some initial value of the T's, or is there hidden dependence on the T's as well?
No. It depends. So that will come just I think on the next slide, hopefully. So what are actually parameters? What are, how we call it? What are canonical variables, right?
So you're saying that the T's are also there, even though you don't denote them?
Yes, sure. So there are T's, and that will come. Yes.
Okay.
Just,
the second question is, this business of the branch points being the only point of the singularity, is this something which follows immediately from the expression, or is that a lot of derivation to prove that?
No, it doesn't follow. It's actually, it just happens, as we'll see. So it just for, that's what I say. It will follow, but not immediately. It will follow from the procedure, just for, so to speak, for your future reference, I would say. So we don't impose this condition. It comes somehow naturally. So then we have the corresponding spectral curve, and on this spectral curve we introduce these two differentials. This is the fundamental. This is actually in the core of the whole structure. So so we have this curve given either, and as we'll see, it was a hyperelliptic curve in one matrix model. It's general algebraic curve in two matrix model, and in many applications, it's just a general curve, can be transcendent curve, whatever. So it's, again,
you're blocking your equations at the bottom with your pens. We can't see the bottom line.
oh yes. It's well, yes. So now you have the whole slide. You're right. Okay, and so we have these two differentials, and we have, I impose just several assumptions. The first, that the derivatives in canonical variables, and I still didn't say what are canonical variables. Maybe, well, we'll see it on, it just, I reserve it for the next two slides. So derivatives in canonical variables do not act on the one differential, on dx. So dx is some, basically we fix it once forever. So the only action is basically on the second differential or on the function y. And the second also important assumption is that if I, oops, why? Where I am. So it's, you know, it's always just press something and it jumps somewhere. You must be very careful with this stuff. Okay, so and second assumption is that if when we do variations, basically the genus of this curve, maximum genus depends on the order of the on the power of the potential. But in principle, it can be any lower genus if you have some double points. So somehow another assumption is that when we do variation, we don't, so we keep these double points. So we don't add new cuts. So the genus, at least of this curve, is not changed, and correspondingly the number of the branch points is not changing upon variations. And again, I must confess, it's just a prescription. It's just our assumptions. We know that possibly in real applications, we have to somehow we have to soften some assumptions in order to get the proper critical behavior. But again, it's not my intention today. So we impose these assumptions and we'll stick to them.
But is the location of branch points allowed to vary?
Yes. Basically, yes. So that's, we'll see. Yes. So we basically, if we don't, well, so again, interesting, Nikita. It's interesting question, because in some applications, when we have what is called the hard edges or rigid walls, we actually fix also the location of these points. So we have, again, there are a whole zoo of theories, so I cannot represent all of them in one talk, but that's also good to remember that we have basically two sorts of these branching points. One sort are dynamical branch points that allows to change, and the other sort are these hard edges which are fixed once forever. But again, I must say that possibly today I will refrain from considering these hard edges and consider only a situation with these dynamical branch points. But at the end of the day, all what I said will be actually adjustable to every situation. So it's more general that I'm about to present today. So consider, let's come back. So first of all, if we have these correlation functions, we also have as asymptotic. It just follows more or less from physics, but it also follows from the consideration with distribution of eigenvalues. If these distribution are finite, then obviously when I go to infinity, they have decreasing asymptotics. And basically we see that if I, again, so I must say again that it's not for differential. So if I wanted to differential, I have to multiply it by the corresponding differentials. It's for the function. So again, it's not exactly. So it's now I come back to function. So as a function, these as a function, these functions have these asymptotics when x goes to infinity, when the corresponding parameter or the corresponding variable. And now crucial observation. So consider now the variation. The variation of this special differential y dx. first consider this variation with respect to SI, and SI were occupation numbers. So I assume first that these SI are independent on the coefficients or times of the potential. So for instance, when we know again from the from our evaluation of this quantity is that it has this asymptotic behavior again as a function. So I slightly I removed dx so far. And what will
Leoinid, sorry,
happen?
you were differentiating with respect to SI without ever defining the SI. Can you give a definition of the SI?
Yeah, so it's it was so SI are here, you see. Well, it's almost SI as twiddle I. So SIs are combinations of this, and this Sj are basically number of eigenvalues, because this is also simultaneously this integral gives the number of eigenvalues of the corresponding matrix inside every interval here.
So this is somehow auxiliary information which you're
It's
adding.
auxiliary. That's what I say. That's something that we impose by hands. It's so if I if I come back to this picture, basically the actual result of integration for actual matrix model that we know, it will be some weighted, not just a single expression, but it will be a sum. It will be a weighted sum of these expressions. That was in Bertrand, Nikolai, and I think Gaetan paper. So that's you. But again, I impose these additional constraints. Yes.
But are they related somehow to the filling fractions?
They are filling fractions, yes.
Okay, but the filling fractions really should be a consequence of your variational integral and not something put in by hand.
Well, again, depends on the angle of view. When we evaluate something, yes. So because so if come back to the original picture, of course, at the end of the day, we need to find also some equilibriums, because it's auxiliary as you see, and that's correct. We have to find also some equilibrium condition for distribution of these filling fractions. So basically, we need to show that, say, basically to find the critical point of this potential with respect to filling fractions. But again, so let me well, it's a fancy story, but really for my consideration today, we have to skip it. Otherwise, well, we cannot make. Oops. So let's consider first this variation. And oops, you see that since this function has this asymptotic expansion when x goes to infinity, if I impose the condition that times of the potential and T naught is a scaled total filling fraction, total number of eigenvalues. They are independent, so when I do variation, both these parts disappear, and this is a regular part, you see, because it's proportional to if I take it with a differential. Everyone knows that it's d1 over x, so it's It's actually a differential of the local variable at infinity. So we see that this derivative correspondingly has no singularities at infinity.
Leonie, may I ask you a question, please?
Yes.
So SI, are they somehow related to T's?
No, they are. That's precisely the idea, that they are independent variables.
Okay, okay. Mhm.
So they actually, I will come to it again in 1 or 2 slides. So they constitute actually the set of canonical variables or flat variables. So there is some flatness condition as well. So let's continue. So now let's see, at the branch point, we have a local coordinate, because the branch point also one more restriction that I didn't mention, but I will mention it right now, is that we also assume that the differentials, slightly funny, but okay, so dx has simple zeros. Simple zeros, and these simple zeros are branch points, well, which we denote by mu alpha. And if we have this structure, then the local coordinate is basically near this branch point is this xi. When I differentiate this expression. So just by derivative, you see it's so it's only acts, this derivative only acts on mu, and so it's just a simple calculation to show that correspondingly, so this is considered to be finite, this derivative, so we are in a outside of critical regime. And you see that the result of this gives me just something regular expression multiplied by dxi. So again, this simple consideration shows us that this derivative is also regular. So basically, this means that the derivative of this differential is regular everywhere. So it's a holomorphic differential itself. And as such, we also know that if I consider these filling fractions, oh, sorry, it must be S. Filling fractions as independent variables, then it's not just a holomorphic differential, it's the abelian canonically normalized differential. So the derivative of these expressions gives an Abel differential, which is pretty much funny. It was well, it's still quite an old story, so it's probably, it appeared in mathematical world, I think, in around the 90s in Igor Krichevar's works. In physical world, it's relevant references probably to Kachaza and Waffe in 2002, and who observed the relevance of Seiberg-Witten equation in matrix models. But let's move. Let's consider the other variations. So because it was only a variation with respect to filling fractions.
Leonie, before just last question about this moment, may I?
Yes, yes.
Yeah. So when you answered to the question of Nikita, you said that yes, this variation might be of the variation just as this branching point could be the parameters of variation. Correct?
It's correct, but it happens that that taking branch points as variables somehow, is not very profitable in some sense.
Yes, but this is why my confusion, that if indeed take the branch point, but branch points mu's, they are depends on t, so they are determined by t's.
Yes.
So s, but you are talking about deformation parameters, that s's are deformation parameters. So
yes, and the other deformation parameter comes on the next slide, because obviously also this TK, and recall that we have that the potential is just a sum TK by K xk. So it's just times or coefficients of the corresponding potential. And they also belong to the set of flat variables. So if we, for instance, again, if we consider the same variation, now the variation of this part, of course, is not zero, but it's some in variable x is some pure pole of some of order actually k plus 1. Yes, and the rest is irregular. So at the branch point we have the and at the branch point it's again regular. So again, now we obtain the differential that is regular everywhere except infinity, where it has a pure pole of some fixed order. And these are differentials or meromorphic Krichyver-Wisdom differentials. So again, we see that, and again, if since these filling fractions, again, I just came from previous life, it's I redefine them as Sj given by these integrals, and if I consider these variables independent, then we have a canonical normalization of the corresponding differentials. So we have the whole system of algebraic structures. And if now, I have to skip something, but we can get all these results out of the representation of the free energy in terms of this equilibrium distribution of eigenvalues given by the spectral curve itself. So it's just a small exercise to derive from this variation formulas on the previous slide, the variation formulas for the free energy itself. And it happens that, well, if I take derivatives with respect to filling fractions, they are given by B-cycle integrals. So this partially answers John's question. So actually, it was known, so to speak, that at least to get the equilibrium distribution of the filling fractions for a given potential, I have to ensure the condition that all integrals over B cycles of this form are zeros. Next, the same free energy satisfy equations of Wisdom-Krichyver hierarchy. And so these are given by some, it will be important in some sense that they also are given by the residue formulas involving this special differential y/dz. And also this will come later in this talk, y/z. So also was a nice story about third derivatives of this potential, because third derivatives of this potential give rise to WDVV systems, or system of WDVV or associativity equations, again based on this canonical variables. I will not probably, because of lack of time, I will not make in any more details. Just move. Oops. And just move down, because we still have to present the main construction, but it's an important building blocks of the main construction for topological recursion. Well, this I have to skip completely, but it just to show you, so you can just have a look at the slides. And I wanted, because it was reserved for the first lecture and I wasn't unable to get to it. So because if we have a two matrix model, it's another example, and two matrix model is given by this integral over two Hermitian matrices with the interaction term of this simple form. And basically it describes, again, it describes the following structure. So the original matrix model was describing the triangulation of the surface. Now imagine that we have triangles of two sorts of basically two colors, like blue and red, and they are distributed somehow randomly. Or we can think about it as a spin 1/2 structure in the corresponding two-dimensional gravity. And we make it, we identify this structure with this matrix model where you see that the edges and vertices are of two sorts. So we have red vertices, red and blue vertices, and they can be joined by the edges that change the color on the boundary. And this is described precisely by this matrix integral above. So again, I will not spend, unfortunately, time now, but you can see in the nutshell, so there are the corresponding transformations that produce the relevant loop equation. So because it will take the rest of this talk to go through that. And you see that, but everyone is welcome to have a look on slides. So at the end of the day, we again have the corresponding algebraic equation. Oops, let me make it. The corresponding algebraic equation, and we again have the identification of variable y, which appear, of course, here. We have an identification of this variable y with the one loop correlation function of one of the matrices. And if we come back to the same structure that we had previously for just one matrix model, so we have now this spectral curve. Again, we introduce a set of A and B cycles, canonical variables, and canonical variables, interestingly, here are just coefficients of just one of the potential. So we also select which potential we have to use to produce canonical variables. Filling fractions basically doesn't depend, because we can instead of y dx we may consider x dy, so we can consider the dual potential. So these filling fractions nevertheless remain the same. And what is interesting is that nevertheless the whole structure that we had for the one matrix model remains relevant in this case. So all differential relations remain exactly the same. So if I have also when I do these variations with respect to filling fractions, I again obtain canonically normalized holomorphic differentials. When I do variations with respect to times, I get again Wisdom-Krichever differentials. So it's these structures, these derivatives, they're very much uniform and doesn't depend, amazingly enough, they just doesn't depend on the details of the corresponding models. So basically having spectral curves, the only dependence in this of these differentials is on the spectral, on the Riemann surface itself, not on the differentials, the particular choice of differentials on this Riemann surface. So this just shows us that we have a very special and I would say almost unique universality property for the corresponding structures. Sorry. So now universality property of two-point correlation function. So first of all, I introduce some notion. So if we have 2 points on the spectral curve, let's consider a special bidifferential. We call it, again, it's just a theorem that nothing is called by the name of a person who invented it. So basically we call it abusively the Bergman bidifferential. Actually, it was probably still in works of Abel. But well,
in Baker's book, it appears under the name of the fundamental quadratic bidifferential.
yes. Otherwise, we have to pronounce all that, John. You're right, because Bergman is much shorter, right?
Yes, but the trouble is that Bergman means an entirely different thing.
It's it's actually well, we know what Bergman means, so it's just it's not entirely different. It's related to this differential. Just
there is a Bergman kernel which is of the form dz bar, and this is not of that form.
yes. No. I agree. I totally agree. That's some abuse of names. Let's call it somehow, nevertheless. Okay, so it's bidifferential that is symmetric with respect to exchange points on the Riemann curve. It's canonically normalized to A cycles, so all integrals over A cycles are zeros. And its only singularity, it's on diagonal when these 2 points coincide, and then it has a double pole. And there are famous Riemann bilinear identities that integral over B cycles of this differential gives exactly this holomorphic differential, and some residue formulas produce the corresponding Krichever-Wisdom differentials. And this actually is fishing for something from this, because now if we consider the action of the loop insertion operator, and remember that this loop insertion operator, it's actually, it adds one differential. And then it's a sum. So I had it before, but I just, so I don't remember, maybe x minus 1 minus k d over dtk. It was on the previous slides. I just don't want to scroll it up and down. So the result of this action combines on this YDZ combines into this simple combination of this Bergman of these bilinear differentials. And if, for example, I acted by the same operator on derivative of the potential, it's easy to evaluate. It produces this simple term, and in a hyperelliptic case, this simple expression itself is a combination of these differentials. And remember that if I want to get to two-point correlation function, I just have to consider the proper linear sum. Actually, I subtract one from another, and you see that these two terms canceled and these two doubled. So we obtain the famous formula that the second order correlation, this two-point correlation function in the leading order is actually, again, so it's not a function anymore. Remember that it's differential by our definitions. And this differential is related to the Bergman, or whatever, how we call it, to this particular famous differential in this simplest ever form. So, and you see that now we completely strip out all information about, all specific information about the curve, because it's pretty much, this differential is pretty much uniform and doesn't depend on details. So we strip all double points, everything. Actually, it was came almost when it's also came from physical community. I remember it was like 25 years ago, or even more. And somehow it came almost like a shock, because it was observed first in different models, and in all these models it was the same result.
Leonid, quick question. Is it true that W2 can also be written as a second partial differential with respect to Vx1 and, or let's say Vx and Vz applied to the partition function?
Yeah, that's true, right?
And that Wn can similarly be written as an nth
Yes,
order.
yes. So they all can be obtained from the partition function.
Okay, I don't want to use up your time, but that connects with my question from the last time. Is the partition function necessarily a tau function? Because that expression, the multiple differential of the partition function with respect to the V's, can be written, can be interpreted if it is a tau function as a multi-current correlation function.
Well, again, it's a good, of course, question, which usually people say when they don't know a good answer. It's, but it's really, certainly it's something deeper that we might be comprehending in this talk. And it depends on the person who you are asking. So again, if you will ask, as you know, if you will ask Bertrand about that, the answer will be yes. But to be honest, so far, how to put it? It depends on the angle of view. So it's I prefer not to speak about tau functions in this talk. Tau functions, namely relevant, related to integrable hierarchies. And on the other hand, possibly we know situations where we don't have an particularly good integral hierarchy. Still, we have some procedures, similar procedures in topological recursion. But one thing is that possibly relevant to your question is the relation between, that's I will not speak about today, but I hope that Gaitan in his series of talks will precisely address this question. It will be a relation between what we call, what will be introduced between global and local models. Possibly it will contain the answer to your question. Okay, John. Okay, but let me just finish, complete the structures. So the next and crucial point is now 3-point correlation function, because now we have precisely now we resort, well, to the variation with respect to branch points. So there was this Rauch variation formulas of 40s of 20th century. How we can vary the Bergman kernel, let's call it this way, with respect to position of branch points. And this Bergman kernel splits into the product of two. And it's actually not a very difficult exercise to obtain from this formula the formula for the action of this loop insertion operator on 2-point correlation function that by definition produces 3-point correlation function. And it happens that it is given by this integral and more precise by the corresponding residue formulas. So in this integral, I do one small thing. I pick up one of these Bergman kernels, doesn't matter which one, and I pick up this differential of y. So here is dy, not just y. And there we are. And I integrate these both parts, because again, our condition is that this dx has a simple zero. So it's just just a normal residue. It's just a simple pole here. So I can freely integrate on these two parts without changing the result. And I introduce this special combination, or not it was basically original Bertrand Einard idea to integrate and to get here this special combination. Why it's so special? Because the same combination appear everywhere. It's a combination that we call a recursion kernel, kernel of the topological recursion. But so far for 3-point correlation function, we have the first appearance of the residue formula. And this recursion kernel is actually inverse to the operation of multiplication by y and evaluating, so basically making some projection, which again I have to put under the carpet, this part of the story. But the relevant part is that indeed this recursion allows us to construct all higher order correlation functions of all orders of expansion out of these simple things, out of this simple data that we have. So basically, the only thing we need is this differential y and the corresponding Bergman kernel. That's it. All the rest can be obtained, can be constructed recursively out of this. So my time is running out, and I will move. So this is just to show there is some nice pictorial representation of this. So for instance, these green arrows indicate the corresponding recursion kernel. Blue lines are Bergman differentials. And this is an example how we can construct how the corresponding loop insertion operator acts on each of these terms. So at the end of the day, we can present this picture. So if I have the corresponding correlation function or correlation differential, I represent it as a sum of action so this is actually so all these so all these boxes inside all these boxes I will consider only as stable correlation functions. The only contribution of non-stable correlation when one of these functions is non-stable is Bergman kernel itself is here. In all other cases they are all stable, and we see that out of that we can construct the correlation function of higher order in number of legs and expansion out of correlation functions of lower order. And I start with the initial conditions. So the only two correlation functions that are not constructed and that we started with are this 3-point correlation function in leading order and the 1-point correlation function in a sub-leading order. So out of these initial conditions, using this procedure, I can construct all correlation functions of all orders. And this is basically what we call the topological recursion itself. And again, I hope that Gaetan in his talks also will present some development of this story and some more some more modern, I would say, insight on all these objects. So before I stop, it's the last slide, basically. I just have this list, so to speak, of properties that we call the topological recursion. So recall that we have this. It starts always with the spectral curve and a set of two meromorphic differentials. Then we have the branch points, and the assumption is that these branch points are actually zeros of dx, and that all zeros are simple. And again, there are series, there are models in which we by Bouchard and NR, when we just relax this condition. Correlation functions, actually not the functions, but differentials, and they admit the asymptotic expansion. And then we have some details: master loop equations, a set of let variables, Zyberg-Witten and Wisem-Krichever relations. This is, of course, also very important conditions. that the second order correlation function is the Bernoulli kernel. Then we have the recursion kernel, and then we construct all higher correlation functions using topological recursion. What is interesting and what is probably also will be relevant in Gaetan's presentation is that there was a mystery that was resolved actually, I think, only by Kontsevich and Soibelman, and recently in 2016, that basically this procedure, by some reason, if I come back to this picture, you see that we have a selected variable here. So the procedure itself, as it's formulated, is not explicitly symmetric, totally symmetric, but it must produce a totally symmetric correlation function at the end. And even we know that each term of this relation is not totally symmetric, only their combination is. So, and I completely skipped this part that we can reconstruct actually the free energy out of one-point correlation function, but it was more than enough today. Sorry for again taking a little more time than was supposed. And well, thank you. So I also draw your attention to this book, which contains many, well, which may be a good book to start with if you want to be familiar with this stuff in more details. Okay, thank you.
Thank you, Leonia. John, you have still a question?
Let me first
just
stop recording and then we will go to the question part.